Hi all, and welcome to part 2 of 3 of C++ for Java Contest Programmers. In this section, we're going to cover functions, and then we're going to cover a couple of containers from the standard template library. So first, let's talk about functions. Here we have two very simple functions. You can probably guess immediately what they do and see the similarities from Java. Add obviously just adds two numbers and returns the sum. The only difference between this and the Java way of doing this is that this is not in a class, it's just a raw function, which you can tell by the lack of a qualifier here. And this is just demonstrating that just like Java, you can have void and return nothing, in which case you're just using the side effects or any pass by reference parameters. Everything in C++ is passed by value. This example should not be particularly surprising to you because even in Java, if you pass a small value like an integer, then that is passed by value, and you would not expect if you did s equals a plus b for that to propagate out to the caller. It turns out though that in C++, even if this was an object, say this was a standard string or something even bigger like a vector, that is also passed by value. And that can have unintended consequences because depending on the class, some modifications you made to it, depending on if the mutator you call in the class references stuff directly in the class, in the shallow level that gets copied, then your mutations are not going to be seen. But if you're doing something like a collection, then it may copy a pointer or a reference to a bunch of memory, and if that happens, then it will mutate. So basically, it's a bad idea, first of all, for semantics, and second, for performance, to pass objects around by value. So the alternative is to pass by reference, and we talked about references at the end of the last talk. So here, we are always worried about performance in this case because, passing an int, passing a pointer, they're about the same size. So this is going to be performance identical to the previous version. But semantically, what this means is we no longer are passing in s. We're passing in an alias to s, a reference. So here, now we're setting the sum into an alias for some other variable. And the alias is not actually to a variable in this function, it's in the caller. So if in the caller we pass in x here, now this does survive the call and we get 3 out. A consequence of this you'll see is that if we were to just put the 9 here and say add 1 to 9, that wouldn't compile because you can't take a reference to a constant. That makes no sense because constants are constants, and if you do this, you're claiming, hey, I can modify this thing. So that's actually a compile error. Some people find this syntax a little annoying. In C, if you were doing this, and you were doing this with pointers, you would actually have a star here to indicate that this was a pointer, and then you would have the ampersand here to indicate you are taking the address of x to pass in. So that gives you some hint that, oh, hey, here I'm passing in something that can be modified. But in C++, this is kind of transparent. This could be s or ampersand s, and from the caller point of view, the syntax is exactly the same, so you don't really know. So it pays to know the prototype, which is what the types are of all the parameters, to know if this is a reference or not. So the other than the semantic problems with passing in bigger things by value, obviously the other bad thing is performance. I mean, say my big struct is something that's not like a handful of bytes. Say this thing is like 4, 8, 16K or something like that, even bigger. Without the reference, the compiler has no choice but to actually copy those bytes into the context of the called function. So all of that stuff is going to get pushed on the stack, and then it's going to have to go through and copy everything. And if you have something where a function is called over and over or recursively, then, I mean, you're adding a bunch of runtime overhead that you don't need. So always, I mean, if you're not dealing with something like a base type, then pass it by reference. And the reason we have const here is to avoid the other problem I was talking about. If you're not intending to change s at all and you're only doing this as a performance optimization, if you put const, it guarantees that you can't accidentally change s down here. Basically, it makes, if you try to do any operation on s that would change it, it's a compile error at this point. Because every method in C++, we're not talking about defining them, but when you do define them, you have to declare, if it doesn't change anything, you can declare it as const, and then it's safe to call from a const reference. So if you try to call a non-const method on a const reference, it's a compile error, and you know you did something that you weren't intending to do. Return values are another matter. So a lot of people see that advice and think, oh, I should use references on my return values as well because they're fast and I don't want to take the hit of copying like this struct back out when I'm done. So they'll either like cheese it by putting my big struct as a parameter in here, and then you're not really using the return value for what it's intended for. You're using a parameter as your return value. Or they'll try to do this. And this is just wrong and won't compile. And the reason is that a reference is an alias to something. And it's a rule of the language that an alias cannot outlive the lifetime of whatever it refers to. So in this case, if you think about this, you allocate an instance of MBS inside here in this function, and presumably between these two lines, you do a bunch of work to put values into it and get it into a reasonable state, and then you return it. Well, you return it, and here you're trying to return it by reference, which means you're returning an alias to it. But as soon as you finish the return statement and go back to the caller, this is out of scope and is destroyed. So the reference is now pointing to nothing. So the compiler just won't let you do that. There's other ways with blocks that you can get into this situation, but these days the compiler is pretty good about letting you know you've made a mistake, which is great because the alternative is a dangling reference, which will just out and out crash your program. So surprisingly, the thing that we said do not do in parameters and use a reference, the exact opposite advice is true for return values. And that's due to something called NRVO, which stands for Named Return Value Optimization. If you think about the semantics of this, what's going on here semantically is we create an MBS, and when we return it, so presumably there's an assignment in the caller that says my MBS equals construct. And then this MBS that we built in here is going to be copied into that variable in the caller, and then the caller can happily go off and use it. Well, that copy is a really bad thing from a performance standpoint if this thing is big. So what the language designers did was they told the compiler vendors, hey, we're going to put in this spec, the compiler is allowed to elide that copy and optimize it away if it's reasonable. And it turns out that with this style of construction, it's a perfectly reasonable thing to do. So what's going to happen here really is my big struct, the caller is going to have created one of those things for the other side of the assignment, and then it's going to call construct. There's going to be a hidden reference that is passed in here. You don't even see it. That's a reference to the caller's copy of this thing. And in this function, MBS is not really on the stack for construct. MBS is a reference to the caller's copy that it once built. So you're going to do all your work here, and you think you're doing this to a stack local variable in construct, but really you're working directly with the caller's memory. And when you're done, guess what? We don't even need to do anything for this because we've already built the thing in the place it's supposed to be in the first place, which is in the caller's copy of my MBS. So that's really nice. And basically it means it's safe to return things from a function, even if they're structs or collections or whatever, because they're not going to get copied. I will note, you won't care for the purposes of contest, this is not true for C. This is a C++ optimization. In C, you should not do this. So now let's talk about some of the standard collections. I'm going to talk about a couple. I'm going to talk about arrays and maps here. The designers of the language went to some effort to try to make the interface to all these things consistent. So if I teach you arrays and I teach you maps, and then you go and look at the references for all of the other collections, and there are quite a few, the interfaces should look very familiar because they try to follow the same design patterns for everything. So here, first we're going to talk about arrays. In the last talk, if you remember, I mentioned C arrays in the context of why you shouldn't use C arrays for strings and some of the bad things that can happen. All of those same arguments apply to arrays in C++ for just other data types besides just characters for strings. So here, obviously, all we're using vector, which is the recommended thing to use for a variable size array. All we're doing here is taking the number of 0 through 9, and we're putting them in a vector, and then we're printing them back out. So let's take this apart piece at a time. Oh, first of all, I will mention here the header vector. I mentioned this back in string. Again, the header file for vector is just vector. So pushback. Push is a standard operation on an array, which just says add it to the end. And we have push back here because there are containers where you can push stuff on the front as well. So this is called push back. If this were a queue, it would just be called push. So this is just appending whatever value of the loop iterator that we're on to the back of the array. So I want to address performance a little bit here because some people will look at this and say, oh, gross. You're just growing this array over and over and over again without trying to figure out how big it is. And yes, you can do that. And yes, you could just manually, and I'll show you how to do this in a bit, make this thing 10 and just use bracket notation. But I wanted to talk about this to show you why the performance actually isn't that bad. So vectors use a standard heuristic for growable memory in general. And that is, if you have a piece of memory that you're adding stuff to, and you reach the capacity that you've allocated already, you don't just allocate one more slot. You actually double the amount of memory you have. And you do that each time. So the size of memory grows exponentially. And the idea is that's kind of like doubling once or twice. I mean, you're going to lose some amount of memory to padding or to fragmentation because you're probably not going to land exactly on a power of 2, but you're going to be somewhere in the neighborhood. If you have a really big array and you double and then you fill that halfway, I mean, you're using like 3/4 of the memory, which is okay. But the reason that's done and that we are willing to put up with that is memory is cheaper than performance. And with that scheme, you're only, because memory grows exponentially, you're only doing a logarithmic on the size, the final size of the vector number of allocations and copies to get there. So if that means if you have, say, 64K elements, 64,000 elements, then you're only going to have allocated and copied 16 times. It's actually going to be less than that because there's some minimal power of 2 that are allocated up front. I think it's 16. And you can prove with recurrence relations if you've already gotten to those, or if not, you will in your classwork. You can prove that amortized, that it is still order 1 to push an element on the array because the cost of that copy amortizes well over all of the pushbacks. So doing this versus manually setting the array size is kind of, it's a tiny bit of performance. Maybe it matters sometimes, but usually not. And here, this is just to show, so we're going to talk about iterators a little bit later, but pretty much all of the containers that you'll see in C++ support something called iterators, which is basically a way of give me the first element, now give me the next element, now give me the next element. And if a container supports the standard C++ way of doing iterators, which is pretty simple, then you can use this shortened version of a for loop to iterate over all of the elements. So here, I is every time through this for loop is just going to be the next successive member of this. So this is just going to print out all the members of the array. The only bad part about this is sometimes when you're iterating over an array or some other container, you want to know where you're at. You want an index variable. Some languages let you actually specify, I want an index and a value in here. Unfortunately, C++ doesn't easily have that. So there's two ways you can do it. You can have a separate index variable that you just increment in the loop, or you can just fall back on this. And there's a method called size on all of the collections. So you can just say I equals 0, I is less than inst.size I++, and then do inst sub I with square brackets in here, just like any other array. One more thing, I forgot to mention, sorry. So I mentioned square brackets. I should really have had a slide on this, sorry. So if you say int square bracket I, as you would in Java to access an array, then that access is not checked. And what that means is if your index is out of bounds, you're going to just get whatever happens to be at that memory location. And this is obviously very, very fast because all you're doing is adding a number to a pointer, possibly multiplying it by the size of whatever's in the array. It's also dangerous because we all know what happens. I mean, accessing an array out of bounds is a common cause of wrong answer. So there are actually two syntaxes here. There's a method called .at. And if you use .at sub I, then you are basically saying, hey, I want to do the exact same thing as square brackets, but check the index for me. And at that point, if I were to do .at 10 in somewhere in here, I would crash. And crashing is while you're testing your program is better than just seeing something that looks right but isn't really. But at obviously is slower, especially if you're accessing the array or not. So whether you use square bracket notation or .at, you can use .at while you're developing your solution to make sure that all your indices are right. But for the purposes of submitting, you probably want to change it to square brackets because that's a lot faster. So maps, or dictionaries as they're called in some languages, basically it's just a way of, hey, here's a key, give me the value back quickly. There are actually two map types, and you want to be clear on which one you're using because performance matters, and this is a performance functionality trade-off. So I mentioned earlier that you can enumerate via iterators over the elements in a container. So standard map enumerates in key order. So if your keys are integers, then you're going to, if you iterate over them, you're going to get them back in the order of the key as an integer value. Strings, same thing. What you pay for that is that things like insert and lookup are log n. Usually, in fact, every implementation I know of, this is implemented as a red-black tree, which if you haven't gotten to that is a balanced binary tree. And in order to do that, you have to, the key has to have a less than operator on it. And we'll get into that when we talk about sort. Typically, if you're using a map, the key you're going to use is either going to be some form of integer or a string. In contest problems, it's very rare that you say, hey, I want to do a standard map and I want to put like my struct in there as a key. But if you do that, you're going to have to do the same thing we're going to talk about in sorting later, and you're going to have to define a less than operator on that on your struct so that map knows how to sort them into the binary tree. So what if you don't care about enumeration in key order? What if all you really care about is putting elements in and getting them out fast? Then you want standard unordered map. And This is a hash map, and that means that on average, you're going to have order 1 lookup and insertion. So by losing that enumeration, and this is probably like the 95% case in contest problems, where all you want to do is store stuff in the map and get it back. You don't really care about walking over the whole thing, or maybe you're just going to do it and you don't care about the order, because you can always sort the thing later in nlogn time if you really need to. Again, because this is a hash table, the key has to be hashable, and all of the standard types in C++ should be like int, long, whatever, string, whatever. You're not going to even have to worry about a hash function or any of those. If you have a struct, you have to write a hash implementation for it. That can be a little trickier. So if you actually do have a situation where you're keen on a struct, you might want to fall back on standard map rather than mess around with trying to come up with a good hash implementation. If there's a good one in your hack pack, then sure, go ahead and use it. So again, the header file for map is just map. If it was unordered map, it would be unordered underscore map. Other than that, and the name of the type, everything I'm going to talk about here, the semantics are identical for, or the syntax is identical for both. We're going to start. We're going to talk about my pets because I love talking about my pets. We are going to start just having a map, and the key is going to be the name of a pet, and the value is going to be their age. So here you can see that you can use just standard square bracket array notation to set something into the map. So if Ripley was already in the map, then her age would be changed to 4. If she was not, then she's going to be inserted into the map, and then her age is going to be set to 4. The only thing you have to be careful about here is if you do a lookup, then here, say Penny was not in the map. This is going to insert Penny with a default constructor for the integer. Unlike other things, this actually initializes to 0, which is nice. As they finally learned that with C++ over C. And so after this, here it kind of looks like we're expecting Penny to be there, but you wouldn't be able to do this if you were trying to test if Penny was already in this map or not. So before we talk about lookup, as an aside, I'm going to talk about another type that's all over the place in the C++ standard library, and that's std_pair. This does not, it's so small it doesn't have its own header. It's just declared anywhere where you have a container that uses it. We'll bring it in for you. And the definition is something very close to this. This is using generics, but I mean, you don't really have to understand the syntax because you're never going to create a generic in contest code. Basically, all I'm trying to show you here is that pair is a struct, and it has a member called first and a member called second, and those are of arbitrary type. When you're dealing with a container, and this obviously, I mean, you don't need this for a vector because the index of a vector is always an integer. But for containers where there's a key and a value, like map and unordered map, this is how things are passed around, where typically U is going to be the type of the key and V is going to be the type of the value, and then therefore first is the key and second is the value when you're manipulating these things. So how do we do lookup if we want to actually know whether something is in the map or not? So there's a method called find. Makes sense, right? So we're going to look up Ripley. We happen to know from 2 slides ago that she is in the map. And find does not actually return directly a pair like I said on the last slide. What it returns is something called an iterator. This is the same object that's actually being used by the for loop we saw earlier when you're going over an entire collection. Under the covers, for is just getting an iterator and using it in the ways we're going to talk about to go over the entire collection. And the type of this iterator is std : map of std : string, int : iterator, which is a mouthful and a ton of stuff to type. So one of the nice things in modern versions of C++ is the keyword auto. Auto tells the compiler, hey, try to do type inference based on the return value here to declare this variable. So people have a love-hate relationship with auto. There are people that go a little bit too nuts with it and say things like auto iter equals 0, and then iter is obviously an integer. But what integer? I mean, is it an int? Is it a long? Is it unsigned? And that depends on the type of constant and whether you've annotated the constant. And really, if it's an int, why not just type int and be specific about it? But this is the scenario that auto was really intended for, because some of these types, and if you can imagine, if you have containers nested in containers, this is going to get even more messy. It's perfectly clear here what we're trying to do. Ages.find is returning an iterator. We don't really care about the type. All that we care about is this is an iterator we can work with. So yeah, this saves you a lot of typing, and actually to me ends up being more clear. So every container has two methods on it called begin and end. And begin gives you an iterator to the first element if there is one, and end gives you an iterator to just past the end of the container. So you can't dereference end to get a value, because end is kind of like null, although it's much safer because it's very well defined in the context of the container. But and obviously if the container is empty and you call begin, you're immediately going to get end. So lookup methods like find use end as a flag to say, hey, this didn't exist in the collection, I couldn't find it. So here, if iter is age's end marker, end iterator, then we have no Ripley, which is very, very sad because Ripley is awesome. Otherwise, iter is going to refer to the entry in this map that talks about Ripley. I just talked about that. So now let's talk about actually using the iterator. And this is where I think the language designers fell down a little bit. And the reason is that iterators have been in the language a very long time, before everything was looking like references like it is now. So an iterator, rather than looking like a reference, they decided to make iterator look like a pointer. And if the standard notation for accessing a member off of a pointer is this arrow operator that you see here. And if you just want to dereference the pointer to whatever value, you put a star in front of it. And actually, you can just put a star in front of an iterator and get back the contents, which would in this case be the pair we talked about. So long story short, you just got to remember that when you're dealing with iterators, you don't use a dot here to dereference it. You use dash greater than, the representation of the arrow, and then whatever member you're looking for in the iterator. Or, I mean, if this was a vector and we're using iterator, star iter would just be an int or whatever the type of the vector was. Here, we're interested in having Ripley have a birthday, so we're incrementing the age. So there's a little bit going on under the covers here that you should understand. So first is going to be Ripley. It's going to be the string Ripley. That is const in the pair for the very simple reason that you might think that if you changed first, that you were changing the map entry and you could rename Ripley to something else. That's not the way it works. And to prevent that confusion, you're not allowed to change first on iterators out of a map. Second, however, I mean, this isn't just an int. This is actually turns out to boil down to a reference to the value type that's inside the map. So age here refers to the actual int in the map data structure. So if we do this increment here, we are actually giving Ripley a birthday inside the map, and since her age was 4 before, after this, the next time we ask for it, we're going to get 5. That's a long worded way of saying that you can actually use second to when you're iterating through a map to mutate the entries in the map. So I talked about this a little bit earlier, but because map returns iterators just like vector returns iterators for begin and end, we can also iterate through the map. So here because we're using a map and not an unordered map, again, we're going to get our pets in alphabetical order. So we're going to get Ripley and then Scratch, whereas unordered map, we would get them in some random order. And then we're going to be able to mess with them. So here you'll notice I've said auto ampersand. So it turns out auto isn't fully auto. You have a little bit of control over the type of the variable that you're going to get back. Here we're asking for a reference to pet, so that that we can actually do stuff with it and modify it. And obviously, if the value type is big, well, actually it don't matter because we'll have a reference anyway. But the type of this would just be the pair instead of a reference to the pair if we didn't do that. We could also put const here to guarantee we're not going to mess with the value if we wanted to, if we were just iterating through. So here you can see, note now, this is not an iterator. This is a reference directly to the pair. So now we can use the familiar dot notation here because we don't have that extra level of indirection that we had that was introduced by the iterator. So I know that's a little annoying and confusing. Unfortunately, it's just the way it is. And again, as I talked about before, first is const. We can't change the name of an animal to XXX because the language won't let us. But here, just as in the previous version, we can do this. We can give everybody a birthday and increment their age in the middle of this loop. So what if we were going through this loop and wanted to delete things? Well, first of all, what if we just want to delete something? And we again have our map, and we want to erase Penny. So there are two ways to do this. One is to just pass in the value. So here we're passing in Penny. If you were in a loop and you had the iterator, then you could also just, or if you had an iterator from find, you could also just pass the iterator here. So if we wanted to delete Ripley here, and instead of having Ripley have a birthday, we wanted to give her away, which I would never do, we could just do ages.erase iter here, and then Ripley would be gone from the collection. This requires a little bit of care in loops, which I will talk about next. So you might have already gotten to what if we are iterating through, and sorry, there should be, this call should have parentheses here. That's a mistake. But here, this is another way of iterating through a collection with the other form of the for loop. So we're going to start at the begin, which, as I had said, is an iterator to the first element. And we're going to go until we hit the end. And you can actually use the way to go to the next element in the collection without having it done under the covers for you is to do plus plus on it. You can also do minus minus if there are multiple classes of iterators. If for a sequential iterator, you can do plus plus minus minus. For a random access iterator, like you'd get out of a vector, you can actually add arbitrary numbers and skip around. So if we are in this loop and we delete an element and then we try to go to the next with plus plus, well, we've just plus plus on an iterator to which the element that we're talking about no longer exists. And that's wrong and is probably going to crash. So erase is defined. If I erase an iterator on any collection, what it returns is the next element in whatever order we're enumerating the collection in as an iterator. So if second is 7 here and we delete some pet because their age is 7, then what iterator is now going to be is if we had plus plus before we did this erase. Well, actually that's not true because that would be this. It's going to be the next thing after this pet, and then we can keep going in our loop. Note we don't want to also plus plus because then we'd be skipping two things. But this is the safe way of looping through a collection and removing things from it. So I have just given you the very, very basics of this. There's a lot more to learn, which you can learn by reading other people's solutions in C++ or going out and searching the stuff online. There's a ton of resources online. cppreference.com is a good site that has documentation for the entire standard library and even tells you what versions of the standards various things exist in and don't. There have been changes over the years even to the semantics of existing stuff. And just to talk about a few of the other things you might run into, set and unordered set are like map, except they are sets, which means they only deal with key and they don't have an associated value. The difference between these two is exactly the same as the difference between a set and a map and an unordered map, and that this will also sort the elements of the set, and this will not if you're enumerating through them. Stack and queue should be obvious. These are just implemented like in terms of an array underneath, but they give you the familiar push and pop semantics that are more clear if you're writing something that like a BFS and you want to use a queue. List is a linked list, and so on and so on. There's actually a ton of them. The iterator semantics and arrays and all of that. And some of them, how to insert is different, but for the most part, will look very, very familiar if you've already been following along with what I've said so far. In the next section, we're going to talk about sorting in I/O, and thanks for watching.